Hello everyone. In this video, we will be discussing an axisymmetric numerical which is completely different from the previous problem what we discussed. Different in the sense like there is no much changes in the applications. The boundary conditions is much different here. Just we'll have you look on the question. So sketch shows a long cylinder of inside diameter 80 mm and outside diameter 120 mm. So inside diameter and outside diameter is given in terms of mm. Snugly fits in a hole over its full length. The cylinder is then subjected to an internal pressure of 2 megapascal. So internally, the pressure is being continuously spreaded to the walls of the cylinder of magnitude 2 megapascal. Using two elements on the 10 mm length shown, find the displacements of the inner radius. So they are asking us to find out the displacement at the inner radius. And the sketch is also given in the question itself. Without much complications, we can go with that. So for the element of 10 mm height, where a 2D element I have taken of rectangular shape, total 4 nodes, which I'll be dividing into two elements, element 1 and element 2. Look at the boundary conditions here. Internally, it is of snugly fits. Snugly fit means something like it could able to move inside properly, but in the y direction it can't able to move. So both node 1 and node 2 it should be fixed in y axis. And moving to this the outer surface where it is fixed properly. Yeah. So node 1 and node 2 we can able to rotate off, but which can't able to move in the y direction. So that is why this y direction arrested symbol is shown here, and at node 3 and node 4 it is fixed properly. And I'll be considering this as my element 1 and this as my element 2. Even it is not compulsory that you should go with this as element, this is element 2. You can go with anything as element 2. And the forces at each node, I'll be writing the corresponding force. Like at node 1 and node 2, the internal pressure is acting on. So it should act in the positive x direction. You can able to see here. And there is no forces is acting on y direction of node 1 and node 2. Similarly, at node 3 and node 4, there is no forces acting on. And since only one side, because it's an axisymmetric element, the distance from the z axis, there is axis of rotation to the exactly where the elements start. This 80 mm, the whole diameter is given, so half will be 40. And similarly, the outer diameter boundaries, where the value is given as 120, so half is 60 mm. Young's modulus given as 200 gigapascal and Poisson ratio given as 0.3. Very interesting problem. And for the past 2-3 years, the same problem are like the change of the numerical. These kind of problems was frequently asked in the university question papers. So do observe this problem carefully. So, before moving to the further steps, let me start the problem with the D matrix. So, D matrix, it is the same D matrix which we have used for solving the previous problem. So, I'll just tell you what is the formula we have to use to calculate the D matrix. Here you can able to see here the formula to calculate the D matrix is Young's modulus divided by 1 plus nu 1 minus 2 nu 1 minus nu 0 nu 1 minus nu 0 nu 1 minus nu 0 0 0 0 1 minus 2 nu by 2. So this is the D formula, and even this is the B formula. So let me first substitute nu value and E value which is given in the question itself. So this is the answer we'll be getting. So what is the answer I'm getting is 2.69 to 10 power 5, 1.15 to 10 power 5, 0, 1.15 to 10 power 5, 1.15 to 10 power 5, 2.69 to 10 power 5, 0, 1.15 to 10 power 5, 0, 0, 0.77 to 10 power 5, 0, 1.15 to 10 power 5, 1.15 to 10 power 5, 0, 2.69 to 10 power 5. This is the D value I'm getting. For both elements, the determinant of J, that is the Jacobian matrix, is 200 mm square and A is 100 mm square. So from the previous equation 6.31, forces F1 and F3 are given by the formula is 2 pi R1 L1 P1 by 2. So I know all the data which is given in the question itself. After substituting, I'll be getting the force as F1 and F3 equal to 2540 Newton. And I'll be using for the whole problem the units as mm and Newton. Then the me matrix relating element strains to nodal displacements are obtained first. For the element 1, first let me find out R dash, which is equal to 1 by 2 of 40 plus 40 plus 60, which is equal to 46.67 mm. Sorry, 1 by 3 also. So I'll be getting B1 for the element 1. I'll be getting the value as minus 0.0500 0.050, and second row 0.10 minus 0.100, third row 0.1 minus 0.05 minus 0.100 0.05, and fourth row 0.00710 0.00710 0.00710. And for element 2, R dash is equal to 1 by 3 of 40 plus 60 plus 60. So I'll be getting 53.33 mm as the average value, and B2, this is the equation I'll be getting. Now we need to multiply B1 and B2 with the D matrix. So the element stress displacement matrices are obtained by multiplying both D and B. So this is the D value and this is the B value. So D is the common value which we have found out in this particular step, and B1 and B2 we have different. So I'll be multiplying D value and B value. Before multiplying, make sure that it is possible to multiply. So it is basically 1, 2, 3, 4. This is a 4 cross 4 matrix, and it is 1, 2, 3, 4, 5, 6. So 4 cross 6 matrix. So 4 cross 4 and 4 cross 6. So we are supposed to get 4 cross 6 matrix. Here 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Yes, we are getting. So it is possible to multiply, and this is the answer we have to get. So again, I suggest all the students to do the manual calculation and do cross verify whether you people are getting the same answers. So DB1 and DB2, this is the answer. Do not want to say the answers. Just have a look on the video. You can pass it and you can just make a note on the answers. Next, the stiffness matrix are obtained by finding 2 pi R dash into A and B transpose into DB for each element. So K1 and K2. It is quite complicated, but no option. You can do one thing, since we know the properties of the global stiffness matrix. First find out the main principal leading diagonal value. Make sure that there is no zero value, there is no negative value, and later start find each row value above the main principal leading diagonal. Later you can just write the corresponding values in the column. First row means the first column value you can write down. For both K1 and K2, same procedure you can able to follow up. But again, I'm telling you, make sure that when you are doing this, you are not calculating even the main principal leading diagonal. It is a waste of time. Go with the calculation of principal leading diagonal and above the principal leading diagonal. Row wise you can calculate off, so that it will be easy for you to do that. So using this elimination approach on assembling the matrices with reference to the degrees of freedom 1 and 3, we get. So we know the degrees of freedom, except two parts, remaining everything is fixed. So that is node 1 and node 4. So ultimately we will be getting node 1 and node 3. So after calculating, we are getting the displacement value as Q1 and Q3 as this one. So stress calculations, we will be following this method. From the set of nodal displacements obtained above, the element nodal displacements Q can be found using the connectivity. Then using stress strain relations and the strain displacement equation, we will be getting the stress equation as D into B into Q matrix, where B dash is nothing but B, and which can be evaluated at the centroid of the element. We also note that sigma theta is a principal stress. The two principal stresses, sigma 1, sigma 2, corresponding to sigma r, sigma z, and tau r z, which can be calculated by using the Morse circle. So with this problem gets completed. If you have any doubt on this particular video, post just